Okay, so let's continue. This next video is about the normal distribution, and this is basically an extension of the standard normal distribution. So we can deal with different kinds of data sets. So our example, let's assume that we collect the weights of males in the United States. So right here the data is weights. And let's assume, which it is, that data is normally distributed with a mean of 190 pounds. So that would be the mean. And the standard deviation, let's assume that is 30 pounds. Right? So that is the mean and the standard deviation. And what we're saying is that this data is normally distributed. So now we're going to answer up a lot of questions about the percentage of males that are below a certain weight and so on. So let's begin with this. So if we select a male at random, what is the probability that the weight of that male is going to be less than, let's say, 200 pounds? All right. So that's the question. In other words, we're asking also is what percentage of males weight less than 200 pounds? Since the mean is 190, we know that this number is going to be bigger than 50%. Let's draw a picture right here that will help us understand the problem. This right here is are the male weights. This is the data set, and this is how the data set is distributed as the density function. The mean is 190, and the standard deviation is 30. And here is 200 to the right of 190. And we want to know is how much data is in here. What percentage of the data is going to be below the 200? So we only have a table where the mean is 0 and the standard deviation is 1. But then we would need a table where the mean is 190 and the standard deviation is 30. The way to resolve this problem is to standardize the data. In other words, we're going to take this data and this graph and convert it into a standard normal distribution by taking the z-score of every value. So that's called standardizing. So we're going to, what is called is to standardize. All right, mathematics, that's called a linear transformation, in which we're basically taking this set and we're going to pack it into a set where the mean is 0 and the standard deviation is 1. The way we do that, this is the standardized data for those weights. The way we do that is we take the z-score of the data values. Remember that the z-score of x is x minus the mean divided by the standard deviation. So if we take the z-score of the mean, it will go to 0. And then we take the z-score of 200. So the z-score of 200 is going to be 200 minus 190 divided by 30. And that gives me 10 divided by 30, which is 1/3, or 0.33, right? 0.33. And remember that what we're after is this area right here. So now what the theory says is that this area is the same as sub 1. In other words, if you get a data set that is normally distributed and you standardize it, which is basically taking the z-score of every value in the data set, we only need to take the z-scores of 2 values. Then the area right here corresponding to the area below the z-score of the 200 and the area that we're looking for are the same. But now we can look at the table. And so if you saw the last video, we can go to the positive table, and for the value of 0.33, the area is what? Is this the positive table? Yes. So now we have a data value which is 0.33. And so we have that the data value is 6293. I mean, we expected that to be more than 50%. So that will be, oh, I forgot already, 6293. So this area right here is 6293. That's the same as that area. So that will be 0.6293. So two ways of saying this. Two ways of writing this answer. We can say that 63% of males weigh less than 200 pounds. Sorry. Or we can say that the probability of selecting a male at random from this population is 0.6293, that the male weighs less than 200 pounds. All right. So let's do another problem. So let's assume we have the same data set. So again, it's a data set of male weights that is normally distributed with a mean of 190, as we said, and a standard deviation of 30. So in this case, we want to find the percentage of males that weigh between, let's say, 185 and 213. All right, so that's the question right here. What percentage of males fall between this range of weights? Or another way of saying that, if we select a male at random of that population that has the mean of 190 and the standard deviation of 30, what is the probability that his weight is going to be between these values? Sorry. Again, let's do the graph of male weights right here. The mean is what? 190. We know that. Now 185 is to the left of 190, and this is not drawn to scale. And 213 is to the right of 190. And basically what we're looking for is these two areas. All right. And again, we don't really have a table to read where the mean is 190 and the standard deviation is 30. So what we need to do is standardize this problem, that we can use the standard normal tables. Standardizes basically means that we're going to take the z-score of every value. The 190 will go to 0. The 213 will go to the z-score of 213, which is 213 minus 190 divided by 30. That gives me, let me do this in my calculator, 213 minus 190 divided by 30 is 0.767. Well, you only need two decimals, 0.766, so that's 0.77, right? So that will be 0.77. And then the z-score 185 is going to be 185 minus 190. See, it's going to be negative to the left of 0. So 185 minus 190 divided by 30. That gives me 0.167, 0.16, so 0.17 negative. Right? And still we want this area. So how we did this before, if you remember? The way that we did it before is we read this whole area. We find what percentage of data values, in this case weights, have a z-score 0.77 or below. So we go to the positive table, agree? So in the positive table, 0.77 is right here. So that's about 78% of the data, 77.94. That means this area is 77.94. I'm sorry about the coughing. So now we want to know what percentage of the data is below this tail right here. So for that we need to read the negative table at 0.17. So the negative table at 0.17 is, what is this? Negative table at 0.17. 0.17, 0.10, 2, 3, 4, 5, 6, 7. That's 43.25% of the data. So this is 43.25, right? And so the answer is going to be 0.7794 minus 0.4325, and that gives me 0.7794 minus 0.4325. That gives me 0.3469, which is about 35% of the data. Okay, so the answer right here of this problem is 0.3469. So again, how we read this? Two ways. We can say that 35% of adult males weigh between 185 and 233, or the chances that we get an adult male from this population, the chances that his weight falls between 185 and 223 is going to be 0.35. So let's do another example with the same data. All right, so let's again, this is our population right here, weights of males, which is normally distributed with a mean of 190 and a standard deviation of 30. All right, and now we want to know is what percentage of males weigh more than 210 pounds. All right, what percentage of males weigh more than 210 pounds? Let's visualize the data. Right here is the weights. They're normally distributed. The mean is 190. Standard deviation is 30. And 210 is right here. And we're looking for this much area right there. All right, so we're looking for a tail area. And you remember that we can either use the complement or the symmetry to find that area, but this is standardized first, so we can use the tables. So the 190 will go to 0. Then we need to find the z-score of 210. The z-score of 210 right here is 210 minus 190 divided by 30, and that is equal to 20 divided by 30. That gives me 0.67. All right, so then I go to the table. So this is what I could do. If I use the positive table and I read it straight out at 0.67, I get the opposite area. So what I'm going to get is this area right here, that area right there. All right, if I just go to the table and get 210, I'm sorry, 0.67, let's find that out what that is. So I go to the positive table, 0.67, let me see, 0.67, 0.60, 2, 3, 4, 5, 6, 7. That's 78. Let me see, so I see that clear. 0.67, that's 7486. 7486. All right, so this area is 7486, but that's not the area that we want. We want the tail area, so that will be 1 minus 0.7486 which is 1 minus 0.7486. 1 minus 0.7486 gives me 0.2514, right? So what percentage of males weigh more than 210 pounds? About 25%, right? So this is really, really good information, and we can find out the percentage of values in a normally distributed data that fall within certain regions, right? Let's do another problem. Sorry. Okay, so another example for the same male weights that are normally distributed with a mean of 190 and a standard deviation of 30. Let's do a challenging problem. Let's assume that we want to know P80, and let's say P90, and also what that means, right? So now what we're really looking for right now is a data value. So now this is a data value. This is a weight, so that 90% of males fall below that particular weight. All right, so this is data. Let's see what we mean by that. So these are the male weights that are normally distributed, right? Again, the mean is 190. Now what we're looking for is what is the weight. Let's look at X, so that the 90% of the males are below that weight. So that means that this area, this percentage of values is going to be 90%. All right, if we standardize this, let's look at a standard normal distribution. Again, this will go to 0, always the mean always goes to 0. This value standardized, we go to the z of x. See the z-score of x, but we don't know x, so we cannot calculate the z-score of x. But we know that the percentage of values below that z-score in the standard normal tables is 0.9. All right, so what I could do is go to the positive table, and in the area section try to get the closest that I can get to 0.9 to get the z corresponding z value. So let's do that. So right here I am in the positive table. I am right now going to work in the area section right here. Okay, this is the area section. The closest that I can get to 0.9 is this 89.97. That is the closest. So let's grab that value. 0.9 is this value right here. Well, what is the z value that corresponds to that? It's going to be 1.28. 1.28 is the closest that I can get to 190. That's a relationship between the z value and the data below it, the percentage of values below it. So that will be 1.28. So this is 1.28. So I have the z-score of x, but I don't really want the z-score of x. What I want is x. But then I know that the z-score of x is x minus the mean divided by standard deviation. Okay, and now I have everything in here in this formula except x, because the z-score of x is 128. The x is the unknown, the mean is 190, and the standard deviation is 30. Right? Let me multiply both sides by 30. I'm trying to solve this equation, so I'm going to multiply both sides by 30. That way it cancels here, so I get that x minus the mean is equal to 30 times 1.28, 30 times 1.28, 38.4. All right, this mean, which is negative, added to both sides, gives me x is 38.4 plus 190. So the x value, finally we got the weight, plus 190. And that gives me 228.4. 228.4. So that's it. That is the weight. So if your weight is 228.4, you can look at these two ways. 90% of the males weight below you, or another way of saying this is that 10% of the males with this little tail weight above you. All right, so you are P90. The 90th percentile is this particular weight, 228. All right, so it's a very interesting problem because a lot of times that's what we're looking for. We're looking for a data value, so a given percentage of data is below that value or above that value. Another interesting problem is the one that this one right here. So let's assume that we have the same data, male weights, normally distributed, mean 190, standard deviation 30, all right? And now what we want to know is 90% of males weight between this value and this value. So fill in the blank. So now what we want to know is we want to get this symmetric interval where we're going to find 90% of the weights of adult males in the United States, right? So so now we're not looking for one X value, we're looking for two. If we graph this thing, these are the weights. This is the distribution. That right here is the mean, which is 190. And we're looking for this value X, this lower value and this upper value, so that this area right here is 90%. Right? So how we do that? How we find these values? Well, let's standardize to try to understand this, but we're going to come up with formulas. So if we standardize, the 190 will go to 0. This upper value will go to the z-score of that value, and this lower value will go to the z-score of that lower value. And those values are the same. The difference is that this is positive and this is negative because we're doing this symmetrically. So one way that we can do this is to find the z value that corresponds to this area in the negative table, because it's a tail. So if this is 90, then in the tails I'm going to have 10% of the data, or in this left tail I'm going to have 5% of the data. 5% of the data, which corresponds to a decimal of 0.05. So what I'm going to do is I'm going to the negative table and get the corresponding z-score for an area of 0.05 to the left. Let's see what that is. So in the negative table, an area of 0.05. I have this with a bunch of stuff here. Let me erase that. Ooh. All right. So I'm cleaning this up so it's easy to read. For an area of 0.05 right here, if I look at this, this value and that value are as far apart of 0.5. So right here they're indicating with this arrow that the value that we're going to use is this one, negative 1.645. So for that particular z value, we're going to use negative 1.645, right? So that is the value. Where are we? Where did it go? Where did it go? Right here. So this number is negative 1.645. So this value will be positive 1.645, right? but we don't want we need these values, but in reality we want the x values. So what are those x values? Well, let's look at this formula again more carefully. That the z-score of x is x minus the mean divided by the standard deviation. If we multiply both sides by sigma, we get that the z-score of x times sigma, the standard deviation, is the difference between the value and the mean. And if we add the mean to both sides, so we get that the x value is really the mean plus z-score of x times the standard deviation. So we have like another formula. So the x value, the upper x value, is going to be the mean plus z-score times standard deviation. And the lower value is going to be the mean of the population minus, because the z-score is negative, z value times the standard deviation, all right? And that's it. So let's find those values. So the upper value of x is the mean, which is 190, the z-score, which is 1.645, and the standard deviation, which is 30. That gives me 1.645. Let me clear this. 1.645 times 30 plus 190. 239.35. 239.35. So that's the upper value. 239.35. What about the lower value? It's the same thing but with a negative right here. So we get 1.645 times 30 negative, and then adding 190, which gives me 140.65. So this is 140.65. Let's go back to the top. 90% of the males weigh between 141, let me approximate to no decimals, 141 and 239. All right? So weigh between 141 and 239 pounds. That's the unit. Okay, very good. So I'm going to stop this video right here. And in essence, what this video was about is to how to deal with problems that are called non-standard distributed. So they're normally distributed, but the mean is not 0 and the standard deviation is not 1. So what we realize is that to be able to use the tables to get the areas that corresponds to percentages of values below that given data value, we need to standardize, which is basically taking the z-score of the data values that are given. Once we have the z-scores, then we can go to the tables and find the areas. We also did a very special problem, which is this last one, in which we want to find out the symmetric intervals, where we find, let's say, 90% of the values of a data set. In this case, when the data is normally distributed, 90% of the values of the data set will have a z-score between negative 1.645 and positive 1.645. Knowing that, we can use that information to z-scores to actually find out the data values. All right, so that's that. We will produce another video on the next topic.